Picture this. It's a normal day 74,000 years ago. You're an early human living somewhere in Africa or maybe southern Asia. You wake up, look for food, tend to your family, watch the sky. Then, thousands of miles away in what we now call Indonesia, the earth splits open. Mount Toba erupts. Not a regular volcanic eruption, not even a big volcanic eruption. The largest volcanic eruption in the past 2 million years. An explosion so massive it makes every disaster in recorded human history look like a firecracker. In an instant, 670 cubic miles of rock and ash blast into the atmosphere. That's enough material to bury the entire United States under 2 feet of debris. The sky goes dark, not for hours, not for days, for years. This is the day everything changed. Today, there are over 8 billion humans living on Earth. We're everywhere. Cities, farms, mountains, deserts, remote islands, frozen tundra. We've built skyscrapers that touch the clouds, sent robots to Mars, created technology that lets you watch this video from literally anywhere on the planet. We dominate Earth like no species ever has. But 74,000 years ago, we almost didn't make it at all. The eruption of Mount Toba triggered what scientists call a volcanic winter. Imagine the worst blizzard you've ever experienced, except it's not snow falling from the sky, it's ash. Thick, choking ash that blocks out the sun and covers everything in grey death. Temperatures plummet, plants die, animals starve, food chains collapse. The world becomes a freezer wrapped in darkness and humanity. We were reduced to maybe 3,000 to 10,000 individuals. Some estimates go even lower. That's not 3 million, not 300,000, just a few thousand people scattered across the entire planet, trying desperately to survive in conditions that were killing everything around them. If you're using this to fall asleep, that's literally why I make these. So subscribe, maybe, and tell me where you are and what time it is. I check the comments and it's like Tokyo at midnight, Toronto at dawn, all at once. Here's what keeps scientists up at night. We weren't the only human species alive back then. There were others, Neanderthals in Europe, Homo erectus in Asia, multiple human species, all struggling to survive the same catastrophic climate shift. But most of them didn't make it. They went extinct, or their populations collapsed so severely they never recovered. So why did we survive? What made our ancestors special? The answer isn't just about toughness or luck, it's about something deeper. Something that happened to us during those volcanic winters that forged modern humanity in ways we're only now beginning to understand. 'Cause here's the really crazy part. The Toba eruption wasn't the only supervolcano event that shaped human evolution. It wasn't even the first. Over the past million years, Earth has been hit by multiple supervolcano eruptions. Each one was a planetary reset button. Each one pushed our ancestors to the absolute brink of extinction, and each one somehow made us stronger. Tonight, we're going to explore 3 of these catastrophic events. The Yellowstone eruption, 640,000 years ago, that happened right when our ancestors were evolving larger brains. The Campanian Ignimbrite eruption, 39,000 years ago, that might have contributed to the extinction of Neanderthals. And Toba, the big one, the eruption that nearly ended human history before it really began. We're going to understand what a supervolcano actually is, and why they're so much more dangerous than regular volcanoes. We're going to walk through what it was like to live through years of darkness and cold. We're going to see how extreme climate stress didn't just test our ancestors, it transformed them. Because here's what the evidence is showing us. Every time Earth threw its worst at humanity, we didn't just survive, we evolved. We became smarter, more cooperative, more adaptable. The volcanic winters that should have killed us instead forged the traits that make us human. Our capacity for complex language, our ability to plan for the future, our talent for working together in large groups, our innovative use of technology. All of it might trace back to those desperate generations who refused to give up when the sky went dark and the world turned to ice. This isn't just ancient history. It's the origin story of everything we are. Every thought you've ever had, every word you've ever spoken, every choice you've ever made, all of it is possible because a few thousand humans survived conditions that killed almost everything else. So let's go back before cities and agriculture, back before written language, back to when humanity was just a handful of people huddled around fires, watching ash fall from a black sky and somehow finding the will to survive another day. The day the sky went dark changed everything, and the story of how we made it through is the most important story ever told. So let's talk about what actually happens when the Earth decides to hit the reset button. Because here's the thing about supervolcanoes. They're not volcanoes in the way most people think of volcanoes. When you picture a volcanic eruption, you probably imagine something like Mount St. Helens or Krakatoa. A mountain building up pressure, exploding dramatically, lava flows, ash clouds, maybe some lightning for effect. Spectacular, yes. Deadly, absolutely. But ultimately localized. The eruption happens, people die in the immediate area, and then life goes on everywhere else. Supervolcanoes don't work like that at all. A supervolcano doesn't build a mountain. It destroys one, or rather, it destroys the entire landscape, leaving behind something that looks like the Earth itself cracked open and swallowed everything for miles around. What you get isn't a cone-shaped peak, it's a caldera, a massive collapsed crater that can span dozens of miles across. Some are so big you can't even tell you're standing inside one. You just think you're in a valley, not realizing you're actually standing in the footprint of one of Earth's most catastrophic events. The classification system geologists use is called the Volcanic Explosivity Index, or VEI. It runs from 0 to 8. Each number represents a tenfold increase in the volume of material erupted. Mount St. Helens in 1980, which killed 57 people and became one of the most famous eruptions in modern history, was a VEI 5. Powerful enough to flatten forests and bury entire valleys in ash. A supervolcano is VEI 8. To qualify as VEI 8, an eruption has to eject at least 1,000 cubic kilometers of material. That's more than 240 cubic miles of rock, magma and ash blasted into the atmosphere. For comparison, Mount St. Helens ejected about 1 cubic kilometer. A supervolcanic eruption releases 1,000 times more material. It's not just a different scale, it's a different category of event entirely. It's like comparing a hand grenade to a nuclear weapon. Both are explosions, sure, but the consequences exist in completely different universes. So what makes these eruptions so impossibly large? It comes down to the magma chamber. Every volcano has one, a pocket of molten rock beneath the Earth's surface where magma accumulates before an eruption. In a normal volcano, these chambers might hold a few cubic kilometers of magma, enough to cause trouble, but not enough to threaten the planet. Supervolcanoes have magma chambers the size of small states. Yellowstone's magma chamber, for example, is estimated to contain somewhere between 200 and 600 cubic kilometers of molten and partially molten rock. It sits roughly 5 to 10 kilometers beneath the surface, a vast underground ocean of magma heated by a massive plume of hot material rising from deep within the Earth's mantle. This plume has been there for millions of years, continuously pumping heat and magma into the chamber above it. For thousands, maybe tens of thousands of years, the magma just sits there, building up, getting hotter, accumulating dissolved gases, mostly water vapor, carbon dioxide, and sulfur dioxide. The rock above it, the crust that's containing all this pressure, it's strong, but it's not infinitely strong. It's been heated from below, weakened, fractured by countless tiny earthquakes. Then one day, something gives. Maybe it's a new surge of magma from below pushing the chamber past its capacity. Maybe it's a major earthquake that fractures the containment rock. Maybe it's just that the gas pressure inside the magma reaches a critical threshold. Whatever the trigger, what happens next is almost unimaginable. The magma chamber depressurizes catastrophically. When the containment fails, the pressure drop is instant. All those dissolved gases that were held in solution by the immense pressure suddenly flash into gas phase. It's like opening a can of soda that's been shaken for 10,000 years. The magma literally explodes into foam, expanding with such violence that it fragments into billions of tiny particles. Superheated ash, each particle carrying enough heat to ignite anything it touches. This ash cloud erupts upward at speeds that can exceed the speed of sound. Within minutes, it reaches the stratosphere, 30 or 40 kilometers up. Within hours, it's spreading around the globe, carried by stratospheric winds that can move material at hundreds of miles per hour. But the real killer isn't the ash, it's the sulfur dioxide. When that magma vaporizes, it releases millions of tons of sulfur dioxide gas. Up in the stratosphere, where there's no rain to wash it out, this sulfur dioxide reacts with water vapor to form sulfuric acid aerosols. Tiny droplets suspended in the air, so small they can stay aloft for years, reflecting sunlight back into space. This is how volcanic winter happens. Those aerosols form a reflective layer around the entire planet. Sunlight that would normally reach the surface and warm the Earth instead bounces back into space. The effect is immediate and global. Within weeks, temperatures start dropping. Within months, they've plummeted by several degrees Celsius. In the worst supervolcanic eruptions, global average temperatures can drop by 10 or even 15 degrees Celsius and stay suppressed for 5 to 10 years. Think about what that means. A temperature drop of 10 degrees doesn't sound like much, right? But we're not talking about a cold snap. We're talking about every place on Earth simultaneously becoming 10 degrees colder year-round for years. Places that used to have growing seasons suddenly don't. Tropical regions become temperate. Temperate regions become subarctic. Rainfall patterns collapse because the energy driving weather systems has been cut by a significant fraction. The photosynthesis equation breaks down. Plants need sunlight to grow. When you reduce incoming solar radiation by 20 or 30%, plant productivity crashes. Not just a little, it collapses. Some estimates suggest primary productivity could drop by 50% or more during the worst years of a volcanic winter. Forests die back, grasslands turn to dust, crops fail completely, and it's not just about the cold and the darkness. The cascade effects multiply and compound. When temperatures drop, water that used to evaporate from the oceans stays there. Less evaporation means less rainfall. Regions that depended on monsoons find the rains failing year after year. Rivers that flowed from mountain snowmelt dry up because it's too cold for the snow to melt during summer. Lakes and wells that sustained communities for generations run dry. Animal populations collapse. Herbivores can't find enough food. Predators starve when their prey disappears. Fish populations crash when algae blooms fail and aquatic ecosystems destabilize. The entire food web from the bottom up disintegrates. For humans or pre-humans living through this, it would have seemed like the world was ending, because in a very real sense, it was. But here's what makes it even worse. The immediate impact zone of a supervolcanic eruption is essentially sterilized. For hundreds of miles around the eruption site, everything dies. Not from the blast, though that kills plenty, but from the pyroclastic flows. These are ground-hugging avalanches of superheated ash and gas that can move at hundreds of miles per hour. Temperatures inside these flows can reach 700 degrees Celsius, hot enough to vaporize water instantly, hot enough to turn forests into charcoal before they even have time to burn. The Toba eruption 74,000 years ago left deposits of ash and pumice up to 600 meters thick near the eruption site. That's 2,000 feet. Imagine a wave of volcanic material as tall as a skyscraper rolling across the landscape, burying everything, sterilizing everything, leaving behind a moonscape where tropical forests once stood. Then there's the ashfall itself. Hundreds of miles downwind, ash falls like snow. Except it's not snow, it's powdered rock. It buries crops, collapses roofs, contaminates water supplies. When it gets wet, it forms a cement-like substance that's almost impossible to remove. Breathe too much of it and it turns to paste in your lungs, causing respiratory failure. The geological record preserves all of this. Ice cores from Greenland and Antarctica show layers of volcanic sulfur corresponding to major eruptions going back hundreds of thousands of years. You can literally see the spike in sulfuric acid preserved in annual layers of ice, marking the year when a supervolcano erupted halfway around the world. These layers tell us how long the aerosols stayed in the atmosphere, how far they spread, how much cooling they caused. Genetic evidence tells an even more dramatic story. When populations crash, they leave a signature in DNA, reduced genetic diversity, specific patterns of mutation, evidence of what biologists call bottleneck events. When researchers analysed human genetic diversity in the 1990s and 2000s, they found something shocking. Modern humans show evidence of a severe population bottleneck around 70,000 to 80,000 years ago. Our genetic diversity is absurdly low compared to other species. All 7 billion humans alive today are more closely related to each other than the few hundred chimpanzees living in a single forest in Tanzania. Something reduced human populations to perhaps as few as 3,000 to 10,000 individuals, maybe much fewer. And the timing matches up almost perfectly with the Toba eruption. Geological ash layers tell the same story. Sediment cores from lakes and ocean floors around the world show a distinctive layer of volcanic ash from the Toba eruption. It's literally a marker horizon that geologists can use to date other features. Everything above the Toba layer is younger than 74,000 years. Everything below is older. The eruption was so massive it left a fingerprint in the geological record that's visible across 3 continents. But here's what's really terrifying about supervolcanoes compared to other global catastrophes. They're worse than asteroid impacts for long-term survival. An asteroid strike is devastating, absolutely. The impact that killed the dinosaurs released more energy than all the nuclear weapons on Earth exploding simultaneously. It triggered earthquakes, mega tsunamis, global firestorms, probably killed 75% of all species on the planet. But it was fast. The immediate destruction happened in hours. The global firestorms lasted weeks. Even the impact winter, the period of darkness and cold caused by ash and soot in the atmosphere, probably only lasted a few years at most. It was apocalyptic, yes, but it was brief. Volcanic winters last longer. much longer. Because the sulfuric acid aerosols stay in the stratosphere for years, continuously reflecting sunlight, continuously suppressing temperatures, there's no quick recovery, no moment when the sky's clear and things go back to normal, just year after year of failed harvests, declining resources, populations shrinking toward extinction. And unlike asteroids, which are random and rare, supervolcanic eruptions are cyclical and predictable. We know where the supervolcanoes are. We can measure their magma chambers, track their earthquake swarms, watch them building toward the next eruption. We just can't do anything to stop them. Yellowstone, in the western United States, has erupted 3 times in the past 2.1 million years. The last eruption was 640,000 years ago. It created the Yellowstone caldera, a collapsed crater that spans about 34 by 45 miles. The eruption ejected about 1,000 cubic kilometers of material, burying much of North America under volcanic ash. Deposits from that eruption have been found as far away as the Gulf of Mexico. Yellowstone's magma chamber is still there, still active, still accumulating magma from the hotspot beneath it. It will erupt again, not tomorrow, probably not for tens of thousands of years, but eventually. Campiflegrei, near Naples, Italy, is another active supervolcano. It's actually showing signs of restlessness right now. The ground in the caldera has risen by about 3 meters since 1970, indicating magma movement below. Earthquake swarms shake the region regularly. Its last major eruption was 39,000 years ago. The Campanian Ignimbrite eruption, which may have contributed to the extinction of Neanderthals in Europe. Lake Toba in Indonesia sits inside the caldera left by the eruption 74,000 years ago. The lake itself is over 60 miles long and 1,000 feet deep in places. The caldera walls tower above it, marking the edges of where the land collapsed after the magma chamber emptied. The system is still active. Smaller eruptions have occurred within the caldera since the major event. The magma chamber is recharging. These aren't ancient history, they're sleeping giants. And the thing is, we have no way to diffuse them. No technology to drain the magma chambers, no engineering solution to prevent the pressure buildup. All we can do is watch and wait, and hope that if one of them wakes up we have enough warning to prepare. But prepare for what exactly? Because when a VEI-8 eruption happens, preparation doesn't mean survival. Not for most people, not even for most communities. What it means is understanding that the world as we know it will end, and something else, something smaller and harder and more desperate will take its place. This is what our ancestors faced, multiple times, and somehow, impossibly, they survived. Not all of them, not even most of them, but enough. Just barely enough to carry forward the genetic and cultural legacy that would eventually become us. But to understand how they did it, we need to go back to the most recent supervolcanic catastrophe our species survived, the eruption that nearly ended humanity before we even had a chance to begin, the Toba eruption, 74,000 years ago. The day the sky went dark and stayed dark for 6 years. Picture this, it's 74,000 years ago. Your ancestors are living in small groups scattered across Africa, Asia, and possibly Europe. They've survived ice ages, droughts, predators, and diseases. They're tough, adaptable, and by this point in human evolution, pretty damn smart. They've been expanding their range, developing new technologies, passing knowledge down through generations. Things are actually going pretty well. And then the mountain explodes. Not just any mountain, Mount Toba, in what's now Sumatra, Indonesia. When it erupted, it didn't just blow its top, it essentially obliterated itself in the largest volcanic event of the past 2 million years. 2,800 cubic kilometers of material ejected into the atmosphere. To put that in perspective, that's roughly 3,000 times more material than Mount St. Helens erupted in 1980. It's enough to bury the entire state of Texas under 3 feet of ash and rock. The explosion was so massive, it created a caldera, a collapsed volcanic crater that's still there today. 100 kilometers long and 30 kilometers wide. That's not a crater. That's a wound in the Earth's surface big enough to be seen from space. The immediate effects were catastrophic, but localized. If you were anywhere near Sumatra, you were simply dead. The pyroclastic flows, superheated clouds of gas and rock moving at hundreds of miles per hour, incinerated everything within 100 miles. The ashfall buried the entire region under meters of volcanic debris. Forests, grasslands, rivers, animals, and any humans unlucky enough to be in the area, all gone in hours. But this was just the beginning. Within days, ash began falling across South Asia. Not just a light dusting. 15 centimeters, about 6 inches, of volcanic ash covering much of India, Pakistan, and the surrounding regions. Imagine what that does to an ecosystem. The ash is toxic, full of sulfur compounds and heavy metals. It kills vegetation on contact. It contaminates water sources. Animals that try to graze on ash-covered plants either starve or get sick from the toxins. Rivers become choked with ash, killing fish and making the water undrinkable. Archaeological sites in India show this layer of ash like a geological bookmark marking the exact moment when Toba erupted. And here's what's chilling. Above that ash layer you find almost nothing. No stone tools, no evidence of human occupation, no signs of life. It's as if someone just erased an entire subcontinent's worth of human populations in an instant. But the real nightmare was just getting started. Within weeks, the atmospheric effects began. All that material ejected into the stratosphere wasn't just ash. It was sulfur dioxide, millions of tons of it. When sulfur dioxide hits the upper atmosphere, it combines with water vapor to create sulfuric acid aerosols. These tiny droplets are incredibly efficient at reflecting sunlight back into space. They create a kind of global mirror that prevents the sun's heat from reaching Earth's surface. The volcanic winter had begun. Now, volcanic winters from smaller eruptions typically last 1, maybe 2 years. Tambora in 1815 created the year without a summer. Krakatoa in 1883 lowered global temperatures for about 18 months. But Toba was operating on a completely different scale. The best climate models suggest the volcanic winter from Toba lasted between 6 and 10 years, maybe longer in some regions. Global temperatures plummeted by 5 to 15 degrees Celsius. In tropical regions, this meant the difference between lush rainforests and something resembling tundra. In temperate zones, it meant permanent winter. In areas that were already cold, it meant conditions so severe that basically nothing could survive. Picture what happens to ecosystems when summer just stops coming. Plants that depend on seasonal warmth fail to reproduce. They can survive a bad year, maybe even 2, but 6 years, 10 years, they go extinct. And when the plants go, the herbivores that depend on them follow. And when the herbivores go, the predators go too. The entire food chain collapses from the bottom up. For humans, this was existential. We're adaptable, sure. We can eat a wide range of foods, survive in different climates, develop technologies to help us cope. But we still need calories. And when the entire ecosystem crashes, calories become the only thing that matters. Every day becomes about finding enough food to survive until tomorrow. Every decision becomes about whether the energy you'll expend getting food is worth more than the energy the food will provide. The genetic evidence for what happened next is written in the DNA of every human alive today. In the 1990s, geneticists studying human mitochondrial DNA, which is passed down only through the mother's line, noticed something weird. Human genetic diversity was strangely low compared to other large mammals. We should have much more variation than we do. It was as if the entire human population had passed through some kind of filter that dramatically reduced our numbers. The technical term is a genetic bottleneck, a period when population size crashes so severely that most genetic lineages go extinct. Only a few survive, and all future populations descend from those few survivors. The genetic signatures of this bottleneck suggested it happened somewhere between 50,000 and 100,000 years ago, right around the time Toba erupted. Now, calculating exact population numbers from genetic data is tricky. You're trying to reconstruct events from 74,000 years ago using statistical models and mutation rates. But the estimates are sobering. Some geneticists think the global human population crashed to as few as 3,000 to 10,000 individuals. Others think it might have been even lower. Think about that. 3 to 10,000 humans, total on the entire planet. That's fewer people than attended your local high school football game, fewer than live in most small towns. These weren't just population centres either. These were scattered remnant populations, small groups of survivors clinging to whatever refuges they could find. Because here's the thing, the volcanic winter didn't affect everywhere equally. Some regions got hit harder than others. The ashfall was concentrated in South Asia, but the temperature drop was global. However, some places had built-in advantages. Coastal regions, for example, were buffered by the ocean's thermal mass. Water holds heat much longer than land, so coastal areas didn't cool as quickly or as severely as inland regions. The archaeological and genetic evidence suggests human survivors clustered in a few key refuge zones. East Africa, particularly along the coast and around the Great Rift Valley lakes, seems to have maintained small populations. The climate models show this region didn't cool as severely as others, and the lakes would have provided relatively stable water sources. The southern coast of Africa was another refuge. Cave sites like Pinnacle Point in South Africa show continuous occupation through the Toba period. The people there were eating shellfish, hunting small game, and somehow hanging on despite the global catastrophe happening around them. Some populations in India may have survived in southern coastal regions. The ashfall was severe, but along the coast marine resources would have been less affected by the temperature drop. If you could live off fish, shellfish and seabirds, you had a chance. But here's what makes the survival story really remarkable. These weren't just random groups of people getting lucky. The evidence suggests the survivors were the ones who had already developed specific survival strategies before Toba hit. The South African coastal populations has been exploiting marine resources for thousands of years. They knew how to read tides, find shellfish beds, catch fish in tidal pools. When the terrestrial ecosystems collapsed, they had a backup food source that kept producing. They had also developed sophisticated tool technologies, backed blades, tiny stone tools that could be hafted onto spears and arrows, heat treatment of stone to improve its flaking properties. This wasn't just innovation. This was advanced manufacturing, systematic production of standardized tools that required planning and technical knowledge. Most importantly, they had developed social systems capable of maintaining cooperation during extreme stress. Archaeological evidence shows these coastal populations maintained long-distance trade networks even during the worst of the volcanic winter. Ochre and other materials moved along the coast, evidence that groups were still communicating, still exchanging goods and probably information. This social cooperation was absolutely critical, because when resources become scarce, societies can go one of two ways. They can fragment, with every group or individual fighting for whatever's left, or they can cooperate more intensely, sharing resources and knowledge to maximize everyone's chance of survival. The survivors chose cooperation, and that choice saved humanity. But not everyone made it. The genetic evidence shows entire population lineages going extinct during this period. People who had been living successfully for thousands of years, whole regional populations with their own genetic signatures, cultural traditions and accumulated knowledge, just disappeared. In South Asia, where the ashfall was heaviest, the archaeological record shows a near-total absence of human occupation for thousands of years after Toba. Whatever populations had been living there either died or fled to more hospitable regions, and many of them probably didn't make it. In Southeast Asia, genetic analysis suggests population crashes and fragmentations that line up with the Toba eruption. Island populations that had been thriving suddenly show evidence of severe bottlenecks or complete replacement by later migrants. Even in Africa, the fossil record shows a dramatic thinning of human populations during this period. Sites that had been continuously occupied for millennia show abandonment or much reduced activity. The 6 to 10 year volcanic winter was followed by a recovery period, but recovery doesn't mean everything went back to normal. The ecosystems that had existed before Toba were gone. New plant and animal communities emerged, but they were different, often less productive than what had been there before, and the human populations that survived had been fundamentally changed by the experience. Now, here's where things get complicated, because not all scientists agree that Toba caused the genetic bottleneck. The dating is right. The genetic bottleneck happened around the same time as the Toba eruption, give or take a few thousand years. The severity matches too. A volcanic winter of 6 to 10 years could absolutely cause the kind of population crash we see in the genetic data. But correlation isn't causation. Some researchers argue the genetic bottleneck might have been caused by other factors that just happened to coincide with Toba. Climate was already unstable 74,000 years ago. Earth was cycling through ice age fluctuations. Maybe the population crash was caused by a particularly severe glacial period, and Toba was just bad timing. Others point out that archaeological sites don't show as much disruption as you'd expect from a global catastrophe. Some Indian sites above the ash layer show continuity of tool traditions, suggesting at least some populations survived locally, rather than being completely wiped out and replaced later. Some geneticists argue the bottleneck might have been less severe than they initially thought. More recent studies using different genetic markers suggest effective population sizes might have been larger, maybe 10,000 to 30,000 individuals rather than the catastrophically low numbers suggested by mitochondrial DNA alone. And some climate scientists question whether the volcanic winter was really severe enough to cause a global population crash. Their models suggest the temperature drop might have been more regional, with some areas recovering quickly while others remained suppressed for longer. But here's the thing. Whether Toba directly caused the bottleneck or merely coincided with an already ongoing population crash doesn't really change the fundamental story. 74,000 years ago, the human population plummeted to a tiny fraction of what it had been. Whether the trigger was volcanic winter, glacial conditions, disease, or some combination of factors, the result was the same. humanity came terrifyingly close to extinction, and the survivors, wherever they were, however many of them there were, had to adapt to conditions unlike anything their ancestors had experienced. They had to develop new strategies, new technologies, new ways of organizing their societies. They had to become, in a very real sense, a new kind of human. The archaeological evidence shows this transformation. In the sites that remain occupied through the Toba period, you start seeing innovations that didn't exist before. More sophisticated tools, evidence of more complex social organization, signs of symbolic behavior, the use of ochre and ornaments that suggest people were thinking about identity and belonging in new ways. This makes evolutionary sense. When populations crash, natural selection intensifies. Every generation faces extreme selective pressure. Individuals with even slight advantages in intelligence, cooperation, or adaptability are much more likely to survive and reproduce. Over hundreds or thousands of years, these advantages accumulate. The humans who emerged from the Toba bottleneck were different from the ones who entered it. They were smarter, more socially sophisticated, better adapted to survive in marginal environments. They had learned lessons about cooperation, about innovation, about the importance of maintaining social networks even during the worst times. They were our ancestors. Every human alive today carries genes that survived those 6 to 10 years of volcanic winter and the desperate millennia that followed. We're all descendants of the survivors, all products of the bottleneck, all evidence that sometimes when everything goes wrong, a few thousand individuals can be tough enough, smart enough, and cooperative enough to keep humanity alive until the world becomes livable again. But the story doesn't end with survival, because what came next changed everything. Those bottleneck survivors weren't just hanging on anymore. They were about to explode across the planet in a wave of expansion that would reshape human evolution and eventually lead to us. Modern humans, the species that would go on to dominate Earth in ways no other organism ever had. The fire had tested them. Now it was time to see what they could build from the ashes. Because here's where the Toba story gets really interesting. We've talked about the catastrophe itself, the volcanic winter that lasted for decades, the near extinction that reduced humanity to maybe 3,000 to 10,000 individuals scattered across Africa and parts of Asia. But we haven't talked about what that kind of pressure does to a species. What happens when survival becomes so difficult that 99% of your population dies off, and the tiny fraction that remains has to cling to existence for thousands of years in a world that's actively trying to kill them? The answer is simple. Evolution goes into overdrive. Think about it like this. In normal times, natural selection is pretty relaxed. Sure, there's competition for mates and resources, but most individuals in most populations manage to survive and reproduce. The selection pressure is there, but it's gentle, gradual. Evolution happens, but it happens slowly. Then comes Toba. Suddenly, survival isn't just difficult, it's borderline impossible. The volcanic winter has destroyed most food sources, temperatures have plummeted, the sun is barely visible through the ash clouds. In this environment, the difference between smart and slightly less smart isn't just about who gets the better territory or more food, it's about who lives and who dies, and not just individuals. Entire groups. This is what evolutionary biologists call a selective sweep. When environmental conditions become harsh enough, only the individuals with the absolute best adaptation survive. Everyone else gets filtered out. And when you maintain that kind of pressure for not just years or decades, but for centuries or millennia, you don't just select for good traits, you select for exceptional ones. The first and most obvious pressure was for raw intelligence. Not the kind of intelligence that helps you remember where you left your keys. The kind that keeps you alive when every single day presents life or death problems that have never been solved before. Your group's usual water source has dried up. Where do you find water in a landscape transformed by volcanic ash? The plants your ancestors relied on for thousands of years have died. What new food sources can you identify, test and exploit without poisoning yourself? The animals you normally hunted have migrated away or gone extinct. How do you track new prey species whose behavior you don't understand? Every one of these problems required innovation, required thinking through solutions that no human had ever thought before. And here's the thing about innovation under survival pressure. You don't get many chances to be wrong. Make a mistake identifying which plants are edible, and your entire group starves. Miscalculate where to find water, and everyone dies of thirst. Fail to figure out how to hunt the new prey species, and you don't get to try again next season. The archaeological record from the post-Toba period shows exactly what this kind of pressure produces. Around 70,000 years ago, right after the eruption, we start seeing an explosion of technological innovation. New tool types appearing in the archaeological record that hadn't existed before. Not just variations on existing designs, but completely novel approaches to solving problems. There are blades, thin, sharp cutting tools struck from carefully prepared stone cores. These required more skill to make than the hand axes that had dominated human toolkits for hundreds of thousands of years, but they were far more efficient. You could get 3 times the cutting edge from the same amount of raw material. In a world where every resource counted, where travelling to find good stone might mean exposing yourself to deadly conditions, that efficiency was the difference between survival and extinction. There are projectile points, evidence of the first throwing spears. Before Toba, humans hunted by getting close to prey with thrusting spears, dangerous, energy-intensive, and requiring you to approach animals that could easily kill you. After Toba, we developed weapons that could kill from a distance. This wasn't just convenient, it was revolutionary. It meant smaller groups could take down larger prey, meant less risk of injury, meant more successful hunts with less energy expenditure. There are scrapers and awls designed for processing hides, suggesting more sophisticated clothing production. When volcanic winter drops temperatures globally by several degrees, and you're living in regions that are now experiencing conditions they've never seen before, the ability to make warm, weatherproof clothing isn't luxury, it's necessity. But the most important innovation wasn't physical, it was cognitive. Somewhere in the crucible of the Toba aftermath, human communication took a quantum leap forward. We developed what linguists call fully modern language. Now, humans before Toba could almost certainly communicate. They probably had words, basic grammar, the ability to share information about immediate threats and opportunities. But the kind of language that could coordinate complex survival strategies, that could transmit detailed technological knowledge from one generation to the next, that could maintain social bonds between scattered groups who might not see each other for months or years, that's a different beast entirely. That kind of language requires massive cognitive infrastructure. You need the ability to think abstractly, to manipulate symbols in your head. You need sophisticated working memory to keep track of complex grammatical structures. You need theory of mind, the ability to understand that other people have thoughts and knowledge different from your own. Most importantly, you need the social motivation to actually use these capabilities, to invest the enormous mental energy required to become truly fluent in a complex communication system. Before Toba, that investment might not have been worth it. Sure, better communication helps, but if you're living in a relatively stable environment with abundant resources and large population groups, you can get by with simpler systems. After Toba, there was no choice. Small groups scattered across devastated landscapes absolutely needed to share information effectively. They needed to teach their children complex survival skills quickly. They needed to maintain alliances with distant groups, coordinating resource sharing and mate exchange. The selection pressure was brutal. Groups whose members could communicate more effectively could coordinate better hunts, could share knowledge about which plants were edible and which were toxic, could warn each other about dangers, could teach their children the hundreds of small tricks and techniques that made the difference between starvation and survival. These groups thrived, relatively speaking. Groups with less effective communication died out. Over just a few thousand years, this pressure refined human language abilities to unprecedented levels. By 60,000 years ago, when modern humans finally began expanding out of Africa, we were capable of the kind of sophisticated verbal communication that would let us eventually develop writing, mathematics, science, everything that we think of as human civilization. But language wasn't the only social adaptation that Toba selected for. The crisis also created unprecedented pressure for cooperation. Here's the thing about surviving in small groups during a global catastrophe. You cannot afford conflicts. You cannot afford individuals who cheat, who steal resources, who refuse to share. In normal times, in large populations, societies can tolerate a certain percentage of free riders, people who take without giving back. There are enough resources and enough people that a few parasites don't doom the whole group. After Toba, there was no margin for error. Groups needed every member pulling their weight. More than that, they needed everyone actively cooperating, sharing information and resources, working together to solve problems that no individual could handle alone. This created what evolutionary biologists call strong group selection. Individual groups were competing against each other for survival, not through warfare, but through the simple challenge of staying alive in a hostile environment. Groups that cooperated more effectively survived. Groups with internal conflicts, with individuals who prioritized their own short-term gain over group survival, went extinct. The genetic evidence supports this. Modern humans show unusual psychological traits that distinguish us from other primates. We have a much stronger tendency toward what psychologists call prosocial behavior. We're more willing to share with non-relatives, more capable of trusting strangers, more motivated by fairness and reciprocity, more uncomfortable with inequality within our groups. These traits don't make sense from a purely individual selection perspective. Sharing resources with unrelated individuals reduces your personal fitness. Trusting strangers opens you up to exploitation. Worrying about fairness when you could just take what you want seems counterproductive. But from a group selection perspective, in an environment where group survival was paramount, these traits are exactly what you'd expect to see. The groups that survived Toba were the ones where individuals had learned to subsume their personal interests to collective survival, and these groups developed social systems to reinforce cooperation. The archaeological record shows evidence of increasingly elaborate gift exchange networks after Toba, shells from coastal regions showing up hundreds of miles inland, stone tools made from raw materials that could only be sourced from specific locations, appearing in sites far from those sources. This wasn't just trade in the economic sense, it was social bonding, groups maintaining relationships through generations by exchanging valuables, creating obligations and alliances that would ensure cooperation when times got hard. This is the foundation of human sociality. Our capacity for large-scale cooperation with non-relatives, for creating and maintaining complex social institutions, for organizing ourselves into groups far larger than anything seen in other primates, all of it traces back to selection, pressures created by catastrophes like Toba. But cooperation alone wasn't enough. You also needed to be smart about what you cooperated on. You needed cognitive flexibility, the ability to rapidly adapt your strategies when conditions changed. Before Toba, human populations had developed what archaeologists call stable cultural traditions, ways of making tools, hunting prey, processing food that persisted relatively unchanged for thousands or even tens of thousands of years. This makes sense in a stable environment. If something works, why change it? But after Toba, stability became a death sentence. The world was changing rapidly and unpredictably. A survival strategy that worked one year might fail catastrophically the next when the climate shifted, or prey populations moved, or plants failed to seed. The populations that survived were the ones capable of behavioral flexibility, capable of abandoning strategies that weren't working and trying new approaches, capable of learning from their mistakes quickly enough that the mistakes didn't kill them, capable of noticing patterns in their environment and adapting their behavior accordingly. This shows up in the archaeological record as increasing diversity in tool types and hunting strategies. Before Toba, sites from the same region over long time periods show remarkable uniformity. Same tool types, same prey species, same processing techniques. After Toba, you see rapid diversification, multiple tool types appearing and disappearing over relatively short timescales, evidence of exploitation of a much wider range of prey species, signs of experimentation with new food processing techniques. This is cultural evolution in fast-forward mode, not just change for its own sake, but adaptive radiation. Populations trying every possible approach to survival and keeping whatever worked. One of the most crucial innovations was fire mastery. Now, humans had been using fire for hundreds of thousands of years before Toba, we know that. But there's a difference between opportunistically using fire started by natural causes and actually controlling it systematically, making fire on demand, managing it for specific purposes, using it not just for warmth and cooking, but as a tool for environmental modification. After Toba, as volcanic winter dropped global temperatures and transformed ecosystems, fire became absolutely essential, not just for warmth, though that was critical in newly frigid environments, but for making otherwise inedible food sources accessible. Many plants become easier to digest when cooked. Toxic compounds break down under heat. Tough fibers soften. Post-Toba populations needed to expand their diets dramatically to survive, and fire was the technology that made that possible. Fire also extended the range of habitable environments. With controlled fire, you could survive in regions that would otherwise be too cold for naked apes from tropical Africa. You could ward off predators at night. You could work after dark, extending the productive hours of each day. Archaeological sites from the post-Toba period show hearths that are larger and more carefully constructed than earlier fire sites. Evidence of fire management becoming more sophisticated, more central to daily life. This ties directly into dietary adaptation. One of the most remarkable things about the post-Toba archaeological record is the dramatic expansion in the range of foods humans were exploiting. Before the catastrophe, human diets were relatively narrow. focused on preferred prey species and familiar plant foods. After Toba, we see evidence of humans eating basically anything that wouldn't kill them, and quite a few things that would, if not prepared properly. Small mammals that wouldn't have been worth pursuing before, when larger prey was available. Shellfish, which require you to live near water and develop extraction techniques. Underground storage organs, roots and tubers that have to be dug up, often requiring special tools and knowledge about when they're available. Even insects, though these rarely preserve in the archaeological record, genetic evidence suggests humans during this period adapted to processing insect proteins. This dietary flexibility required innovation at every level. New hunting techniques for new prey species. Some of the earliest evidence of trap building comes from this period. Humans figuring out they could capture small animals without expending the energy of active pursuit. New gathering strategies. Learning the seasonal patterns of plant resources in transformed environments. Understanding which plants were worth the effort to collect and process. New processing techniques, especially for toxic plants that needed elaborate preparation to become edible. Crushing, soaking, heating, fermenting, all techniques for breaking down plant defenses and making nutrients accessible, and most importantly, food storage innovation. In times of scarcity, the ability to preserve excess food from good times to sustain you through bad times becomes critical. We start seeing evidence of deliberate drying of meat and fish, smoking techniques, underground caches where food could be stored in cool conditions. These innovations sound simple, but they represent sophisticated understanding of biology, decay, seasons, planning. What's emerging from the post-Toba archaeological and genetic record is a picture of humans who had been fundamentally transformed by crisis, not just slightly adapted, completely reforged. The populations that emerged from the Toba bottleneck were smarter, more cooperative, more flexible, more innovative than the populations that went into it. They had to be. Nothing less could have survived. And all of these adaptations, these cognitive and social and technological innovations, they weren't just useful for surviving volcanic winters. They were pre-adaptations for everything that came after, for expanding into new continents, for developing agriculture, for building civilizations. Every major achievement of human history rests on foundations that were laid during the desperate centuries after Toba, when survival meant innovating or dying. We are, all of us, descendants of the most crisis-adapted species in planetary history. Our intelligence, our language, our capacity for cooperation and innovation, these aren't accidental features. They're the legacy of ancestors who survived the unsurvivable, who looked at a world that was trying to kill them and decided to outthink it instead. But before we get to Toba, before we talk about the most famous supervolcano eruption in human history, we need to go back further, much further. Because Toba wasn't the first time a supervolcano nearly reset the clock on human evolution. That honour belongs to a mountain that most people today know as a peaceful tourist destination, Yellowstone National Park. 640,000 years ago, it tried to end the world. Picture this. You're standing in what will one day be Wyoming, but right now it's just wilderness. Endless grasslands stretching to the horizon, broken by forests of conifers that would seem familiar to modern eyes. Herds of massive animals move across the plains, giant bison, twice the size of modern ones. Camels, yes, camels in North America, saber-toothed cats prowling the edges of the herds. And watching all of this from the edge of a forest, a small group of beings that don't quite look human, but aren't quite apes either. They're Homo heidelbergensis. Your ancestors, though they wouldn't recognize you and you definitely wouldn't recognize them, heavily built with thick brow ridges and faces that project forward. But their brains are almost as large as yours. They're using sophisticated stone tools. They're hunting cooperatively. They're controlling fire. They're talking to each other in some form of language, though we'll never know what it sounded like. These aren't modern humans. They won't become modern humans for another 300,000 years. But they're on their way. They're the species that would eventually split into 3 lineages, one staying in Africa and evolving into us, another moving into Europe and becoming Neanderthals, a third spreading across Asia as Denisovans. Right now, in this moment, 640,000 years ago, they're just trying to survive another day in a world full of predators and prey, dangers and opportunities, and they have absolutely no idea what's about to happen. Beneath their feet, beneath the grasslands and forests, beneath the mountains visible on the western horizon, something has been building for hundreds of thousands of years. A bubble of molten rock the size of a major city, pushing upward against the Earth's crust, heating, expanding, building pressure like a champagne bottle shaken by a giant. These signs would have been there for years before the eruption. Earthquakes, hundreds of them, growing stronger and more frequent. Geysers and hot springs bursting from the ground in places they'd never been before. Animals acting strangely, migrating away from certain areas for no obvious reason. Those Heidelbergensis groups living nearest to what would become Yellowstone probably noticed something was wrong. Maybe their shamans or leaders interpreted it as spiritual warnings. Maybe they decided to move their camps to safer territory, or maybe they just figured it was normal, part of the Earth's regular cycles. They would have been catastrophically wrong. When the Yellowstone supervolcano finally erupted, it released more than 1,000 cubic kilometers of material. To put that in perspective, Mount St. Helens erupted with less than 1 cubic kilometer. Krakatoa, which you've probably heard of because its 1883 eruption was one of the most violent in recorded history, produced about 20 cubic kilometers. Yellowstone was 50 times larger than Krakatoa. It wasn't an eruption. It was a continent dying. The first sign would have been the earthquakes. Not the minor tremors they'd been experiencing, but ground-shaking violence that knocked people off their feet. Trees toppling, rocks sliding down slopes. Then the sound. A roar so deep and loud it would have been felt more than heard. A sound that seemed to come from everywhere at once, from the earth itself. And then the ground opened, not slowly, not with warning. Just suddenly, catastrophically, a crack dozens of miles long tearing across the landscape as the magma chamber emptied itself into the sky. Imagine standing anywhere within 100 miles of that. You wouldn't see the eruption. You wouldn't have time. The pyroclastic flows, avalanches of superheated gas and rock moving at hundreds of miles per hour, would reach you in minutes. Everything within that radius died instantly. Every animal, every plant, every microbe. The landscape itself was scoured down to bedrock, then buried under hundreds of feet of ash and pumice. But the real horror was just beginning. All that material, those 1,000 cubic kilometers of rock and ash, it went up, into the atmosphere, carried by the heat of the eruption itself, rising into the stratosphere where the winds could carry it across the entire planet. Within days, ash was falling on what would become the East Coast thousands of miles away. Within weeks, the ash cloud had circled the globe, blotting out the sun from North America to Asia. Now here's where it gets really bad for those Heidelbergensis populations. They had spread out by this time from Africa into Europe and Western Asia, maybe even into Eastern Asia. They were doing well, relatively speaking. Climate was stable. Resources were plentiful. Populations were growing. They had no concept of supervolcanoes, no geological understanding that would have let them prepare for what was coming. The ashfall came first. If you were in North America, you were already dead, buried under hundreds of feet of hot ash. But if you were in Europe or Asia, you watched the sky turn dark. First a haze like smoke from distant fires, then thicker until the sun became a dim red disk, then darkness, complete total darkness that lasted for weeks. The ash fell like snow, but it wasn't cold and white. It was hot and grey, and it got into everything. Into the water supplies, poisoning them, into the lungs of animals, killing them, onto the leaves as plants, smothering them. But the ash was just the opening act. The real killer was the volcanic winter that followed. All that material in the stratosphere blocked sunlight from reaching the Earth's surface. Temperatures plummeted. Global average temperatures probably dropped by 10 to 15 degrees Celsius within the first year. That might not sound like much, but remember, we're talking about average temperatures. In some regions, particularly in the northern latitudes, temperatures dropped by 20 or 30 degrees. Summers became like winters. Winters became uninhabitable. The growing season for plants collapsed. Grasslands that had supported massive herds of herbivores turned brown and died. The herbivores starved. The predators that hunted them starved. And the Heidelbergiensis groups that depended on hunting those animals, they started starving too. The volcanic winter lasted for decades, not years. Decades. Some estimates suggest significant cooling persisted for a century or more. Imagine trying to maintain a hunter-gatherer society in those conditions. Every winter knowing that spring might not bring relief. Every child born into a world colder than their parents remembered. Every generation watching their hunting territories become less productive, their water sources become less reliable, their survival become less certain. The archaeological record from this period tells a grim story. Fossil sites show dramatic changes in hominin distribution right around the time of the Yellowstone eruption. Populations that had been thriving in certain regions simply disappear from the record. Not gradually, not over thousands of years, but suddenly within a few generations. Some of this is probably preservation bias. Maybe those groups moved rather than going extinct. But the simplest explanation is usually the right one. They died. Entire populations gone. Evolutionary lines that had survived for hundreds of thousands of years, terminated by a volcanic winter they had no way to predict or prevent. In North America, the devastation was even more complete. The fossil record shows massive extinction events among the megafauna. Giant ground sloths, multiple species of horses, certain types of camels, all show signs of dramatic population crashes right at the 640,000 year mark. Some of these species recovered eventually, others went extinct entirely. The ecosystem was completely reorganized, transformed from one stable state to another. But here's what's fascinating. Some Heidelbergensis populations survived. We know this because we're here, because those lineages continued, eventually giving rise to Neanderthals, Denisovans, and us. So how did they do it? The same way humans have always survived catastrophe. They moved. The genetic and fossil evidence suggests dramatic population movements in the aftermath of the Yellowstone eruption. Groups that had been living in the northern latitudes, now uninhabitable, moved south. Populations that had been separated for thousands of years came back into contact, competing for resources in the shrinking zones where survival was still possible. This created exactly the conditions under which natural selection works fastest. Massive environmental stress, reduced population sizes, competition for limited resources. Any genetic variation that provided even a slight survival advantage would be strongly selected for. Better cold tolerance, more efficient food processing, enhanced cognitive abilities for problem solving, improved social cooperation. The survivors weren't just lucky. They were the individuals whose genes gave them the best chance to survive impossible conditions. And there's something else the eruption did. Something that might have been even more important than the immediate survival pressure. It disrupted migration patterns. Before Yellowstone, Heidelbergensis groups had been slowly spreading out, colonizing new territories, maintaining loose contact with each other through trade and occasional interbreeding. After the eruption, those networks were shattered. Populations that had been connected became isolated. Groups that had been similar began diverging. This is exactly the setup for speciation. Take one population, split it into isolated groups, expose each group to different environmental pressures, and wait. Over hundreds of thousands of years, those groups will become different from each other. Different enough that if they meet again, they might not be able to interbreed anymore. They'll have become separate species. The Yellowstone eruption probably accelerated this process. The African populations relatively sheltered from the worst effects because they were further from the eruption and in lower latitudes continued evolving along one path. The European populations, hammered by the volcanic winter, adapted to cold and seasonal environments, setting the stage for Neanderthals. The Asian populations, spread across diverse environments from tropical Southeast Asia to the Siberian steppes, developed their own unique adaptations, eventually becoming Denisovans. None of this happened quickly. Speciation takes hundreds of thousands of years. But the Yellowstone eruption created conditions that made divergence more likely, more rapid, more complete. It was one of several major volcanic events and climate crises that shaped our evolution, but it might have been the one that set the stage for everything that followed. The volcanic winter also contributed to the broader climate patterns of the Pleistocene. The ice ages that dominated the last 2 million years of Earth's history weren't caused by volcanoes alone. The primary driver was orbital mechanics, the way Earth's tilt and orbit changed over thousands of years, affecting how much solar radiation reached different latitudes. But volcanic eruptions, especially supervolcanic ones like Yellowstone, could trigger or deepen ice age cycles. They could turn a period of cooling into a glaciation event that lasted thousands of years. The Yellowstone eruption of 640,000 years ago hit during a period of climate instability, and there's evidence it helped trigger a major glaciation event. Ice sheets that had been retreating began advancing again. Sea levels dropped, coastlines shifted. The world became colder, drier, and more hostile. For Heidelbergensis populations already stressed by the immediate effects of the eruption, this long-term cooling created ongoing pressure that persisted for thousands of generations. They couldn't just wait out the volcanic winter and return to normal. Normal had changed. The world had changed. They had to change with it, or die. Most died. The population crash following Yellowstone must have been severe, though we'll never know exact numbers. But some survived, some adapted, some became us. And 640,000 years later, we're still here. Still carrying genes that were selected for during that volcanic winter. Still bearing the evolutionary legacy of ancestors who refused to give up when the sky went dark and the world turned cold. But Yellowstone wasn't the last time a supervolcano would threaten human existence, not by a long shot. because 566,000 years later, another supervolcano was getting ready to erupt. And this time, it would push our species to the absolute brink of extinction. This time, it would be Toba. Now fast forward, way forward, past the bottleneck, past the divergence of human species, past hundreds of thousands of years of separate evolution. We're coming to 39,000 years ago. Modern humans have already left Africa. They've spread across the Middle East and into Europe, and they're encountering their cousins, the Neanderthals. By this point, Neanderthals had been living in Europe for over 300,000 years. They were perfectly adapted to Ice Age conditions. They had sophisticated tools, complex social structures, even art. Archaeological sites show they created jewellery, buried their dead with care, and possibly even made music. These weren't primitive brutes. These were successful humans who had survived multiple glacial cycles, adapted to the harshest conditions Europe could throw at them, and they were losing, not quickly, not obviously. But the archaeological record shows a slow, steady decline in Neanderthal populations starting around 50,000 years ago. Their territories were shrinking. Sites that had been continuously occupied for thousands of years were being abandoned. The population was thinning out. Modern humans, meanwhile, were expanding. Every century they pushed a little further into Neanderthal territory, not through warfare necessarily, though there probably was some violence, mostly through simple demographic pressure. Modern humans had slightly larger social groups, slightly more efficient hunting techniques, slightly better long-distance communication networks, small advantages that added up over thousands of years. But the Neanderthals were still holding on, still maintaining populations across southern Europe, from Spain through Italy to the Balkans and beyond. They had refuges, territories where they remained dominant, where their specialized adaptations to European conditions gave them advantages over the newcomers. And then the mountain exploded. The mountain was Campi Flegrei, which translates beautifully as burning fields. It sits just west of modern Naples in southern Italy. Today it's a caldera, a collapsed volcanic crater filled with towns and suburbs where 500,000 people live, mostly unaware they're residing inside one of the most dangerous volcanic systems on Earth. 39,000 years ago, it unleashed hell. This wasn't like most volcanic eruptions. Most volcanoes are polite enough to erupt from a single cone, a single mountain. When Campi Flegrei went up, it erupted from multiple vents simultaneously across an area of over 100 square kilometers. The ground didn't just crack open in one place, it shattered like broken glass, with magma fountaining from dozens of locations at once. The eruption column reached 44 kilometers into the stratosphere. That's well above the altitude where commercial jets fly, up where the air is so thin that nothing can survive. And it stayed there, not for hours but for days, maybe weeks, pumping out ash, sulfur dioxide and volcanic gases in quantities that defy comprehension. Volcanologists call it the Campanian Ignimbrite eruption. Ignimbrite is a technical term for the deposits left by pyroclastic flows, those superheated avalanches of gas and rock that move faster than sound and incinerate everything in their path. The Campanian Ignimbrite is the largest explosive volcanic event Europe has experienced in the last 200,000 years. The numbers are staggering. The eruption ejected roughly 300 cubic kilometers of material. That's enough to bury the entire state of Texas under 0.5 meter of volcanic debris. The Volcanic Explosivity Index, which measures eruption magnitude on a logarithmic scale like the Richter scale for earthquakes, rates it as a VI 7. the second highest category, the same magnitude as the Tambora eruption of 1815, which caused the year without a summer and global crop failures that killed tens of thousands of people. But the Campanian Ignimbrite was worse, much worse, because the modern humans and Neanderthals living in Europe didn't have agriculture to fail. They were hunter-gatherers, completely dependent on wild animal populations and seasonal plant resources, and those were about to collapse. The immediate effects were catastrophic. Southern Italy ceased to exist as a habitable environment. Pyroclastic flows buried everything within 80 kilometers of the eruption center, under deposits up to 100 meters thick. That's a 33-story building made of searingly hot ash and pumice. Anyone caught in the flow zone died instantly. No warning, no escape, just the ground shaking, and then a wall of superheated death racing toward them faster than they could run. But the real killer was the ash. Volcanic ash isn't like fireplace ash. It's tiny fragments of volcanic glass, razor-sharp particles that can destroy lungs, contaminate water, and kill vegetation. The Campanian eruption produced so much ash that it blanketed Eastern Europe and Russia under deposits up to 1 meter thick in some areas. Think about what that means. You're a Neanderthal family living in what's now Romania. You've survived the Ice Age for generations. You know where the reindeer migrate, where to find water in summer, where the caves offer shelter in winter. Your ancestors have lived in this territory for thousands of years. Then the sky goes dark, not sunset dark. Midday, midnight. The sun vanishes behind a grey curtain that seems to extend forever in every direction, and it starts raining ash. Fine at first, like dirty snow, but it doesn't stop. It falls for days, then weeks, accumulating on the ground, covering the grasslands where the reindeer graze, filling the streams where you collect water, seeping into every crack and crevice of your shelter cave. The temperature drops, fast. Volcanic aerosols in the stratosphere are reflecting sunlight back into space, preventing it from warming the Earth's surface. Within months, average temperatures across Europe have fallen by 2 to 3 degrees Celsius. That might not sound like much, but you're already living in Ice Age conditions. This pushes you past the edge of what's survivable. The animals start dying first. Reindeer, horses, bison, all the large herbivores that form the basis of the Neanderthal diet. They can't find food under the ash blanket. Grasslands that had supported herds of thousands are reduced to lifeless grey deserts. The animals either starve or migrate, moving away from the devastated zones toward territories that are already occupied, already at carrying capacity. The Neanderthals follow the animals. They have no choice. But now they're entering territories claimed by other groups. Maybe other Neanderthals who aren't interested in sharing resources that are already scarce. Maybe modern humans who have been slowly expanding into these regions for thousands of years. The competition intensifies. Archaeological sites from this period show evidence of increasing violence, more weapons, more defensive positions, more traumatic injuries on human skeletons. The relatively peaceful coexistence that had characterized the early contact period between Neanderthals and modern humans was breaking down. The volcanic winter was creating a zero-sum game where one group's survival might mean another group's extinction. But here's where the story gets really interesting. The volcanic winter hit both species. Modern humans and Neanderthals were both affected by the same ashfall, the same temperature drop, the same collapse in food resources. So why did one species survive and the other begin its final decline? The answer lies in the subtle advantages modern humans had developed during their long evolution in Africa. Remember, modern humans were the descendants of populations that had survived the genetic bottleneck, who have been refined by hundreds of thousands of years of climate variability in Africa. They had developed specific adaptations that seemed minor under normal conditions but became critical during crisis. First, social networks. Modern humans maintained larger social groups and more extensive trade networks than Neanderthals. Archaeological evidence shows that modern human groups were exchanging materials and information across distances of hundreds of kilometers. Obsidian from volcanic sources in Hungary shows up in modern human sites in southern Germany. Shell beads from the Mediterranean appear in modern human sites along the Danube River. This meant modern humans could call on a wider network of support during the crisis. When local resources collapsed, they knew where to find refuge. They had relationships with groups in unaffected areas. They could migrate to territories where they would be welcomed rather than attacked. Neanderthals had social networks too, but they seemed to have been more localized. Their territories were smaller, their groups more isolated. When the volcanic winter hit, they had fewer options, fewer places to go, fewer allies to turn to. Second, technology. Modern humans were using slightly more sophisticated hunting techniques. They had developed atlatls, spear throwers that extended the range and power of thrown spears. This allowed them to hunt from safer distances and take down prey more efficiently. They were also using a wider variety of trap and snare technologies, ways to catch animals without direct confrontation. Most importantly, modern humans seem to have been better at exploiting diverse food sources. Archaeological sites show they were eating fish, birds, small mammals, and plant foods more systematically than Neanderthals, who remained focused primarily on large game. When the herds disappeared during the volcanic winter, modern humans could switch to alternative resources. Neanderthals, specialized for hunting large Ice Age mammals, faced starvation. Third, adaptability. This is the hardest to quantify, but might be the most important factor. Modern humans seem to have been psychologically and culturally more flexible than Neanderthals. They adapted their toolkits more quickly when conditions changed. They abandoned unsuccessful strategies faster. They were more willing to migrate long distances in search of better territories. Neanderthals, after 300,000 years of successful adaptation to European conditions, may have been victims of their own specialization. They had perfected a particular way of life that worked brilliantly under normal Ice Age conditions. But the volcanic winter wasn't normal. It required rapid innovation and adaptation, the willingness to abandon traditional territories and traditional practices. The archaeological evidence for this population-level divergence is stark. In the regions most heavily affected by the Campanian ashfall, Eastern Europe and the northern Balkans, Neanderthal sites show a sudden, dramatic decline. Places that had been continuously occupied for thousands of years were abandoned within a few generations of the eruption. The last Neanderthal artifacts appear, and then nothing. The sites remain empty for centuries. Meanwhile, modern human sites in the same regions either persist or recover quickly. There's disruption, certainly. Some sites are abandoned, but others show continuous occupation right through the volcanic winter period, and modern human sites begin appearing in territories that had previously been exclusively Neanderthal. One particularly telling example comes from the Carpathian Mountains in Romania. Before the Campanian eruption, the region was dominated by Neanderthal populations. Multiple cave sites show typical Neanderthal stone tools, animal bones from large game hunting, evidence of their specialized Ice Age lifestyle. The last Neanderthal artifacts at these sites date to approximately 39,000 years ago. right when the volcano erupted. After the eruption, there's a gap of several hundred years where the caves appear to be empty. Then modern human artifacts start appearing. Different tool traditions, different hunting patterns, different ways of using the landscape. The Neanderthals never came back. This pattern repeats across Eastern Europe. The Campanian ashfall maps almost perfectly onto the regions where Neanderthal populations declined most rapidly. The areas with the thickest ash deposits are the areas where Neanderthals disappeared first. Now, we have to be careful here. Correlation doesn't prove causation. Just because the volcanic eruption and Neanderthal decline happened at the same time doesn't automatically mean one caused the other. And indeed, many anthropologists argue that the Campanian eruption was just one factor among many contributing to Neanderthal extinction. The Neanderthals were already declining before the eruption. Their populations were already shrinking, their territories already contracting. They were already facing demographic pressure from expanding modern human populations. The volcanic winter might have been the final blow, but it wasn't the only blow. Think of it like this. The Neanderthals were a patient already weakened by chronic illness. The volcanic eruption was a sudden acute infection. Would the patient have died anyway? Maybe. But the infection certainly accelerated the process, possibly turned a long decline into a rapid collapse. The population density difference was critical here. Modern humans, with their larger social groups and more extensive networks, had what biologists call population resilience. When disaster struck one group, others could provide support, send migrants to repopulate devastated areas, share resources until local populations recovered. Neanderthals, with smaller, more isolated populations, lacked this resilience. When a local group was wiped out by the volcanic winter, it stayed wiped out. No replacement migration, no recovery, just an empty territory that would eventually be colonized by modern humans moving in from less affected areas. It's like the difference between a large corporation and a small business during an economic crisis. The corporation has reserves, multiple revenue streams, the ability to absorb losses in one department while others continue operating. The small business lives on tight margins. One major disruption can mean bankruptcy. The Campanian eruption created that major disruption. And the Neanderthals, despite their hundreds of thousands of years of successful adaptation, despite their intelligence and culture and sophisticated technology, couldn't recover. Within 10,000 years of the eruption, Neanderthals had vanished from Eastern Europe entirely. Within 20,000 years they were gone from most of Europe. By 30,000 years ago they were reduced to tiny refuge populations in southern Spain and perhaps isolated pockets in the Caucasus Mountains. And then, around 39,000 to 40,000 years ago, the last Neanderthal died. The volcanic winter didn't kill them all directly. No single disaster could wipe out a species distributed across an entire continent. But it tipped the balance. It accelerated existing trends, turned a gradual decline into a rapid collapse, eliminated the refuges where Neanderthal populations might have survived and recovered. And it left modern humans as the last human species standing in Europe. Not necessarily because we were better in any absolute sense, but because we had the right combination of adaptations for surviving the specific crisis the Campanian eruption created. Larger social networks, more flexible technology, greater dietary diversity, higher population density. None of these were massive advantages under normal conditions. But during the volcanic winter, they made the difference between survival and extinction. We are the descendants of the survivors. Again, just as we carry genes from the populations that survived the Toba eruption 74,000 years, ago, just as we carry genetic signatures of the bottleneck that nearly destroyed our species 900,000 years ago, we carry the legacy of those modern humans who outlasted the Campanian volcanic winter while their Neanderthal cousins disappeared into extinction. But we also carry Neanderthal genes, because before the end, before the volcanic winter pushed them past the point of no return, our species interbred. Modern humans and Neanderthals had children together, and those children survived, reproduced, passed on a mixture of both species' genes. Today, everyone of non-African descent carries approximately 2% Neanderthal DNA. Genes that helped our ancestors survive in Ice Age Europe, genes for immune function, skin pigmentation, cold tolerance. The Neanderthals went extinct as a distinct species, but part of them lives on in us. So when we talk about the Campanian eruption and the Neanderthal question, we're really talking about ourselves, about how volcanic catastrophe shaped which genes survived and which were lost, about how random geological events can determine the fate of entire species, no matter how well adapted, no matter how intelligent, no matter how long they've successfully survived. The Neanderthals did everything right. They survived in Europe for 300,000 years, through multiple ice ages, through massive climate fluctuations, and then a mountain exploded at exactly the wrong time, in exactly the wrong place, and suddenly their specializations became liabilities, their adaptations became weaknesses, their refuges became death traps. That's the real lesson of the Campanian eruption. Survival isn't just about being well adapted to your environment. It's about being adaptable when your environment suddenly transforms into something completely different. It's about having the social networks, the population density, the technological flexibility to weather catastrophes that come out of nowhere and reshape your entire world in a matter of weeks. The Neanderthals were incredibly successful humans, but in the end they weren't quite flexible enough, quite connected enough, quite adaptable enough to survive when the sky went dark and the earth itself turned against them. We were, barely, but barely is enough. So you've survived the volcanic winter. You're part of that lucky handful, descendants of maybe a few thousand individuals who made it through when millions died. The ash has settled, the skies have cleared, animals are returning to territories that had been dead zones for generations. And you might think, okay, crisis over, time to rebuild, time to get back to normal. But here's the thing, there is no normal to get back to. Those years, decades, centuries of survival at the edge of extinction, they didn't just kill most of your species, they fundamentally rewrote what it means to be human. Because when you squeeze a population down to a few thousand individuals, scatter them across whatever, refugees can support life and keep them there for generation after generation, you're not just reducing numbers. You're creating what geneticists call a founder effect. And the founder effect is one of the most powerful forces in evolution. Think of it like this. Imagine you have a bag of marbles, thousands of them in dozens of different colours. That's your pre-bottleneck population. Lots of genetic diversity, lots of variation, lots of different traits floating around in the gene pool. Now take out just a handful of marbles. Maybe you get mostly blues and greens, with just a couple reds and yellows. That handful, those are your survivors. When they reproduce and multiply, every new generation is going to be descended from that limited set of genes. The colours that didn't make it into your handful, they're gone forever. But the colours that did make it, even the rare ones, they can become common simply because they happen to be in a survivor's DNA. This is exactly what happened to humanity after each volcanic winter. Every human alive today carries the genetic signature of these bottlenecks. We're all descended from tiny populations of survivors, and our DNA shows it. Modern genetic analysis reveals something stunning. Humans have less genetic diversity than chimpanzees, even though there are billions of us and only a few 100,000 of them. We should have massively more variation, but we don't. Because somewhere in our past our population crashed so severely that we lost most of our genetic diversity and never got it back. The Toba eruption 74,000 years ago is the most dramatic example. Genetic studies suggest that the entire human population might have dropped to as few as 3,000 to 10,000 individuals. Some researchers think it might have been even lower. For comparison, there are more than 3,000 tigers alive today. We came closer to extinction than tigers are right now. But different groups survived in different places, and this is where things get really interesting. Because each refuge, each pocket of survival, created its own unique evolutionary pressures. Groups that survived in coastal areas developed different traits than groups that survived in the interior highlands. Populations that made it through by fishing and gathering shellfish evolved differently than populations that survived by hunting and scavenging. When the crisis ended and populations began to recover and expand, they carried these regional adaptations with them. Groups from coastal refugees spread along coastlines, bringing with them genes that help process seafood diets and resist diseases common in humid environments. Highland survivors descended into lowlands carrying genes for efficient oxygen processing and resistance to altitude sickness. Desert refuge populations expanded across arid zones with genetic variants that help them conserve water and tolerate heat. This is why modern human populations show distinct regional characteristics despite our overall genetic similarity. Not because we evolved separately for millions of years, but because small groups adapted to specific refuge environments during the bottlenecks, then spread those adaptations when the world became livable again. The genetic evidence is everywhere once you know how to look for it. Populations in Southeast Asia carry genetic variants that suggest their ancestors survived near coastlines, possibly island refuges where seafood remained available even when terrestrial resources collapsed. European populations show genetic signatures indicating their ancestors survived in southern refuges, places where Mediterranean climates provided stable environments even during volcanic winters. African populations, the most genetically diverse humans on Earth, show evidence of multiple refuge populations surviving in different parts of the continent, then mixing when conditions improved. But the bottlenecks didn't just shape our genes. They shaped our minds, our cultures, our very conception of the world. Because populations that went through these catastrophes would have preserved memories of them. Not detailed historical accounts, obviously. We're talking about events tens of thousands of years before writing. But cultural memory, stories passed down generation after generation, slowly transforming into myth. Look at the flood myths. Every major culture has them. The biblical flood, Gilgamesh, the Hindu Matsya Purana, Chinese legends of Gunyu, Aboriginal Australian Dreamtime stories of the Great Flood, Greek myths of Deucalion, Mesoamerican flood legends. They're everywhere, and they all describe the same basic story. The world was destroyed by water, or darkness, or catastrophe. Only a few people survived. They repopulated the earth. Now some of these myths might describe actual local floods, rising sea levels at the end of the Ice Age, Mediterranean basin flooding, regional disasters preserved in cultural memory. But the sheer universality of the catastrophe myth, the consistent theme of near-total destruction, followed by renewal from a tiny group of survivors, that suggest something deeper. These might be cultural echoes of the volcanic winters, distorted, mythologized, but preserving a fundamental truth. Our ancestors survived when almost everything died. The darkness, the cold, the years without summer, these would have been seared into cultural memory. As generations passed, the stories would change. Volcanic winter becomes flood, becomes divine punishment, becomes creation myth. But the core remains. We are the descendants of survivors. We are the people who made it through when the world ended. And here's where the paradox appears. The very disasters that almost destroyed us made us more powerful than we'd ever been before. Around 50,000 to 40,000 years ago, something extraordinary happened in human culture. Archaeologists call it the Upper Paleolithic Revolution, but that dry academic term doesn't capture the magnitude of what occurred. Suddenly, human sites across Africa, Europe and Asia explode with evidence of sophisticated symbolic thinking. Cave paintings appear, not crude sketches, but sophisticated art showing perspective, movement, narrative. The caves at Chauvet, Lascaux, Altamira. These aren't the first attempts at art. They're masterpieces created by people who'd been perfecting these skills for generations. Carved figurines emerge. The Venus figurines found across Europe, depicting female forms in sometimes realistic, sometimes stylized ways. Musical instruments appear. Bone flutes that could play complex melodies. Elaborate burial practices become common, with bodies carefully placed and accompanied by grave goods, jewelry, beads made from shells traded across hundreds of miles, specialized tools designed for specific purposes, needles for sewing clothing, spear throwers that let hunters project weapons with unprecedented force and accuracy. This wasn't just technological advancement. This was a cognitive revolution. Humans were thinking in symbols, creating meaning beyond mere survival, developing complex cultures that could accumulate and transmit knowledge across generations. But why then? Why did modern human culture explode 40,000 years ago instead of 400,000 years ago? The answer might be the bottlenecks. Each volcanic winter killed most humans, but the survivors were the smartest, most adaptable, most innovative individuals. They were the people who could figure out how to survive when everything they knew about survival stopped working. Generation after generation, crisis after crisis, natural selection was favoring intelligence, creativity, the ability to innovate under pressure. By the time the population recovered from the Toba bottleneck, humans weren't just numerous again, they were cognitively enhanced. They had been through an evolutionary forge that selected ruthlessly for mental capability. The populations that expanded after 60,000 years ago weren't the same as the populations that had existed before. They were smarter, more creative, better at symbolic thinking, better at planning for the future, and they proved it by conquering the planet. Within 20,000 years of the Toba bottleneck, modern humans had spread from Africa to Australia, from the Middle East to Western Europe, from Southeast Asia to Siberia. They crossed oceans, climbed mountains, survived in deserts and rainforests and frozen tundra. They encountered other human species, Neanderthals and Denisovans and others, and they either interbred with them or outcompeted them or both. The genetic evidence of this expansion is written in our DNA. When scientists analyze human genomes from around the world, they can trace migration patterns going back tens of thousands of years, and what they find is stunning. All non-African populations descend from a single expansion out of Africa around 60,000 years ago. Maybe a few hundred individuals crossing from the Horn of Africa into Arabia, then spreading across Asia, into Europe, eventually reaching Australia and the Americas. This is why all humans outside Africa carry a small amount of Neanderthal DNA. Because our ancestors encountered Neanderthals in the Middle East and interbred with them. Some populations also carry Denisovan DNA, evidence that our ancestors met and interbred with them too, as they spread across Asia. But here's what's remarkable. Despite spreading across the entire planet, despite adapting to radically different environments, despite tens of thousands of years of separate evolution, we remained one species. Because the bottlenecks had created a kind of genetic unity. We'd been through the same evolutionary crucible. We'd been refined by the same selective pressures. We were all products of the same near-extinction events. Modern genetic studies reveal multiple bottlenecks in human history. Not just Toba 74,000 years ago, but earlier events too. Population crashes around 190,000 years ago, 135,000 years ago, 70,000 years ago. Each time the population dropped dramatically, then recovered and expanded. Each time the survivors were the ones best adapted to survive catastrophe. This creates a stunning realization. Every human alive today is descended from people who survived multiple near-extinction events. We're not just survivors. We're the products of repeated evolutionary refinement. Our ancestors made it through disasters that killed almost everyone, multiple times. The genes we carry, the cognitive abilities we possess, the social instincts that let us cooperate in massive groups, these aren't accidents. They're adaptations forged by crisis. This is the paradox of progress. The worst things that happened to our species made us more capable than we'd ever been. The volcanic winters that almost destroyed humanity created the selection pressure that turned us into the most adaptable, most cognitively sophisticated species in Earth's history. But it wasn't just about individuals being smarter. It was about groups being more cooperative. Because you can't survive catastrophe alone. The humans who made it through the volcanic winters were the ones who could work together, share resources, maintain social bonds even when resources were desperately scarce. They were the ones who could pass knowledge from generation to generation, building on what previous survivors had learned. This is why humans today are so intensely social compared to other species, why we feel such strong emotional responses to stories, why we create elaborate systems of shared meaning, religions and ideologies and national identities. These aren't luxuries that appeared after we achieved security. They're survival traits, forged when cooperation meant the difference between extinction and survival. The genetic legacy is equally profound. Modern humans show evidence of rapid evolution in genes related to brain function, immune response, and stress tolerance. These changes happen too fast to be explained by gradual evolution. They're the signature of strong selection pressure. Crisis selecting for specific traits, generation after generation, until they became fixed in the population. Genes related to cognitive function show evidence of recent selection. Variants that increase brain efficiency, improve memory, enhance problem-solving ability. These weren't random mutations drifting through the population. They were survival advantages, selected for when intelligence made the difference between life and death. Immune system genes show similar patterns. Humans have unusually diverse immune responses compared to other primates. This suggests our ancestors survived multiple epidemic diseases, probably during bottleneck periods when populations were dense enough for diseases to spread rapidly, but small enough that only the most disease-resistant individuals survived. Even our stress responses show evidence of selection during bottlenecks. Modern humans have complex hormonal systems for dealing with stress, capable of ramping up to handle emergencies then returning to baseline when the crisis passes. These systems are almost certainly adaptations to repeated environmental catastrophes, allowing our ancestors to maintain function during disasters without burning out. And perhaps most remarkably, we show evidence of selection for what anthropologists call prosocial behavior, genetic variants that increase empathy, promote cooperation, encourage altruism. These traits wouldn't necessarily be advantageous under normal circumstances. Selfish individuals often outcompete cooperative ones when resources are abundant. But during bottlenecks, when survival requires cooperation, when small groups need to work together to make it through, prosocial traits become intensely advantageous. This is why humans today are so much more cooperative than our closest relatives. Chimpanzees cooperate, but in small groups and with constant jockeying for status. Bonobos are more peaceful, but still limited in their social complexity. Humans can cooperate in groups of millions, with complete strangers, based on shared symbols and identities. This isn't normal for primates. It's a specific adaptation to surviving repeated catastrophes that required unprecedented levels of cooperation. So when you look at modern humanity, when you see our cities and technologies and complex societies, you're not just seeing the products of civilization, you're seeing the legacy of volcanic winters, you're seeing the result of near-extinction events that killed almost everyone but refined the survivors into something extraordinary. We are all descendants of bottleneck survivors, all products of the forge, all carrying genes that made it through when billions of others didn't. The very fact that you exist means your ancestors were tough enough, smart enough, cooperative enough to survive when almost everything died. And that legacy shapes everything about us, our intelligence, our social nature, our ability to adapt to new environments, our tendency to preserve and transmit knowledge, even our myths and stories about catastrophe and renewal. These aren't separate from our evolutionary history. They are our evolutionary history, written in genes and culture and the very structure of our minds. The volcanic winters didn't just shape human evolution, they created modern humanity. We are, quite literally, the people forged by fire and ice, refined by catastrophe, survivors of the worst disasters in our species' history. And now, as we face new challenges, climate change and pandemics and environmental degradation, it's worth remembering where we came from. We're the descendants of people who survived the unsurvivable. We carry their genes, their adaptations, their stubborn refusal to give up when everything seemed hopeless. That's not just our history, it's who we are. So here we are, sitting at our computers, watching videos about ancient disasters, living comfortable lives in our climate-controlled homes with our endless food supply and our global communication networks. It's easy to think we're somehow immune to the kind of catastrophes that nearly wiped out our ancestors. We have technology, science, satellites that can watch the planet from space. We're safe, right? Wrong. Because here's the uncomfortable truth. Right now, at this exact moment, there are approximately 20 known supervolcanoes on Earth. Most of them are being actively monitored by geologists and volcanologists who are watching, waiting, trying to predict when the next one will blow. And it's not a question of if, it's a question of when. Let's start with the most famous one, Yellowstone. You've probably heard about it, maybe even visited the park, walked past the geysers and hot springs without really thinking about what they represent. Those beautiful thermal features aren't just tourist attractions. They're warning signs, evidence that just 5 to 8 miles beneath your feet, there's a chamber of molten rock roughly 37 miles long, 18 miles wide, and 5 miles deep. That's enough magma to fill the Grand Canyon 11 times over. And it's active. Modern monitoring technology at Yellowstone is incredibly sophisticated. Scientists have deployed networks of seismometers that can detect ground movement smaller than a human hair's width. GPS stations track how the ground surface rises and falls as magma shifts beneath it. Satellite radar measures minute changes in elevation across the entire caldera. Gas sensors sample the volcanic emissions, looking for changes in chemistry that might signal rising magma. We're watching this thing with technology that would have seemed like science fiction just 50 years ago. And you know what? All that technology tells us? The caldera is breathing, rising and falling, sometimes by several inches per year. Earthquake swarms happen regularly, hundreds or thousands of small tremors as rock fractures and magma moves through underground channels. Gas emissions vary, showing that the system is dynamic, alive, constantly changing. In 2014, a steamboat geyser that had been dormant for years suddenly reactivated. It's been erupting regularly ever since, sending columns of water and steam 300 feet into the air. Nobody knows exactly what triggered this reactivation, but it's a reminder that the Yellowstone system is anything but stable. The last super eruption at Yellowstone happened 640,000 years ago. The average interval between Yellowstone super eruptions is about 600,000 to 800,000 years, which means we're right in the window when the next one could happen. Could be tomorrow, could be 100,000 years from now, but it's coming, and Yellowstone isn't alone. There's Toba in Indonesia, still showing signs of volcanic activity 74,000 years after its last super eruption. Campiflegrei near Naples, Italy, where ground deformation and earthquake activity have been increasing steadily for decades. The Taupo Volcanic Zone in New Zealand, Long Valley Caldera in California, Valles Caldera in New Mexico, Lake Toba, Ara Caldera in Japan. Every continent except Antarctica has at least one supervolcano, and they're all capable of producing eruptions similar to the ones that nearly destroyed humanity. Statistical analysis of volcanic eruptions over the past 2 million years suggests that super eruptions happen somewhere on Earth every 17,000 to 100,000 years on average. The last confirmed super eruption was Toba, 74,000 years ago, which means we're well within the expected time frame for the next one. In fact, we might be overdue. Now, some scientists argue that we're actually less vulnerable today than our ancestors were. We have technology, warning systems, the ability to stockpile food and resources. We could see it coming and prepare. Maybe. But here's the thing about modern civilization. We're simultaneously more capable and more fragile than any human society that has ever existed. Those scattered groups of 20 or 30 people who survived the ancient supervolcanoes, they were vulnerable as individuals, but resilient as a network. Kill one group and a dozen others kept going. Our ancestors lived in what population biologists call a heterogeneous environment with distributed risk. No single catastrophe could destroy them all. We've done the exact opposite. We've created a global civilization so interconnected that disruptions anywhere can cascade everywhere. Our food system depends on industrial agriculture, which depends on reliable weather, which depends on stable climate. Our economy depends on global supply chains that move goods thousands of miles from where they're produced to where they're consumed. Our communication systems depend on satellites, electrical grids, server farms, Our entire way of life depends on stability, predictability, the continuation of the conditions that have existed for roughly the past 10,000 years. A super eruption would shatter all of that within weeks. Imagine this scenario. It's not science fiction. It's based on actual scientific modelling of what would happen if, say, Yellowstone erupted tomorrow at the same scale as its eruption 640,000 years ago. The eruption itself would be catastrophic for North America. Everything within 500 miles of Yellowstone would be buried under feet of ash within hours. Most of the western United States would become uninhabitable. Major cities like Denver, Salt Lake City, Boise, gone under meters of volcanic debris. But that's just the beginning. Within days, the ash plume would circle the globe, carried by atmospheric currents. Air travel would cease worldwide. Jet engines can't function when they're sucking in volcanic glass and rock particles. The entire aviation industry would shut down. Then comes the volcanic winter. Sulfur dioxide in the stratosphere converting to sulfuric acid aerosols, blocking sunlight, dropping global temperatures by 5 to 15 degrees Celsius within months. Agricultural collapse follows inevitably. Plants can't photosynthesize without sunlight. Even in regions that don't receive significant ashfall, crop yields would plummet. Within a single growing season, global food production could drop by 70% or more. The economic disruption would make the Great Depression look like a minor recession. Supply chains built on just-in-time delivery would collapse immediately. Store shelves would empty within days. Fuel supplies would become scarce as refineries struggled with contaminated inputs and transportation networks failed. Modern electrical grids, already vulnerable to disruption, would fail in regions experiencing significant ashfall. All those solar panels we've installed as clean energy, useless when covered in ash and the sky's gone dark. And the psychological impact. Modern societies have no cultural memory of how to survive without the systems we've built. How many people today could feed themselves if grocery stores closed? How many could keep warm without natural gas or electricity? How many even have the skills to purify water without modern infrastructure? We've traded resilience for efficiency, and in a crisis scenario like a super eruption, efficiency means nothing when the systems it depends on have failed. But here's where the story of our ancestors becomes incredibly relevant, because they survived multiple times, under worse conditions than we'd face even with a modern super eruption, and they survived not because they had technology, but because they had something more fundamental. They had adaptability, cooperation, and an absolutely stubborn refusal to give up. Every person alive today carries the genetic legacy of those survivors. The genes that got us through 117,000 years of near extinction, through volcanic winters that lasted decades, through climate disruptions that made vast regions uninhabitable. Those genes didn't disappear. They're still there, still part of our biological inheritance. We are the descendants of the most successful survivors in human history, and we've kept evolving culturally. The same intelligence that helped our ancestors develop better tools and more sophisticated social organization, we've applied that to understanding the planet itself. We know more about volcanoes than any previous generation. We understand the mechanisms, the warning signs, the physics of eruption. We can't prevent them, but we can prepare for them. Scientists studying modern supervolcanoes have identified several key indicators that might give us warning before a major eruption. Increased seismic activity, not just random earthquakes, but specific patterns that indicate magma movement. Ground deformation that accelerates and spreads beyond normal variation. Changes in gas emissions, particularly increases in carbon dioxide and sulfur dioxide. Thermal anomalies detected by satellite imagery, showing rising temperatures in surface features. If we're watching closely, and we are, we might get months or even years of warning before a super eruption. Time enough to prepare, at least partially. The challenge is what we do with that warning. Modern disaster planning for volcanic supereruptions is frankly inadequate. Most government emergency plans focus on conventional disasters, hurricanes, earthquakes, normal volcanic eruptions. Very few have seriously gamed out what happens when you need to evacuate entire regions and prepare for multi-year global climate disruption. The logistical challenges are almost unimaginable. Where do you move 50 million people when the western United States becomes uninhabitable? How do you maintain social order when people realize the food supply is going to fail? How do you allocate scarce resources when everyone needs them equally? But there are things we could do. Food stockpiling programs, not just government warehouses, but distributed reserves maintained at regional and local levels. Development of crop varieties that can tolerate reduced sunlight and lower temperatures. Investment in greenhouse agriculture that could continue producing food even under volcanic winter conditions. Hardening of critical infrastructure against ashfall and climate disruption. Creation of seed banks and genetic repositories to preserve agricultural diversity. Most importantly, rebuilding the kind of community resilience that kept our ancestors alive. Distributed networks that can function when the larger system fails. We can also learn from the volcanic winters themselves, because they're not just ancient history. They're remarkably good models for understanding rapid climate disruption of any kind. And right now, we're conducting our own unplanned experiment with rapid climate change. Not from volcanic eruptions, but from greenhouse gas emissions. The mechanisms are different, the timescales are different, but the fundamental challenge is the same. How do human societies adapt when the climate conditions they depend on change faster than agricultural and social systems can adjust? The volcanic winters our ancestors survived teach us several crucial lessons. First, the disruption happens faster than you think possible. Modern climate models suggest gradual warming over decades and centuries, but volcanic winters show us that when conditions shift dramatically, ecosystems can collapse within a single growing season. There's no gentle adjustment period. Second, the most vulnerable aren't necessarily the people closest to the initial disaster. After Toba, it wasn't just Southeast Asians who suffered. It was populations thousands of miles away who suddenly faced crop failures and ecosystem collapse. Global systems mean global impacts. Third, and most importantly, survival depends less on individual toughness than on social cooperation. The groups that made it through the bottleneck weren't necessarily the strongest or the smartest as individuals. They were the ones who figured out how to work together, share resources, maintain knowledge transfer across generations. They were the ones who built networks resilient enough to absorb local failures without collapsing entirely. In a volcanic winter, in a climate crisis, in any large-scale environmental disruption, cooperation beats competition every single time. And there's reason for hope in that lesson. Because humans are really, really good at cooperation. It's our superpower, the evolutionary advantage that let us survive when other species went extinct. We can coordinate action across vast distances. We can share information at scales that would have been impossible for our ancestors. We can mobilize resources and solve problems collectively in ways no other species can match. When we choose to use those abilities, we're extraordinarily capable. The challenge is choosing to use them. Because right now, We're not preparing for the next super eruption with anything like the seriousness it deserves. We're not building the resilient systems we'd need to survive multi-year climate disruption. We're not even having serious public conversations about what it would mean to face a volcanic winter in the modern world. We're acting like it can't happen. Or maybe like we're too advanced, too technologically sophisticated for nature to threaten us the way it threatened our ancestors. But the volcanoes don't care about our technology. They don't care about our sophistication. They operate on geological timescales, building pressure, moving magma, working toward the inevitable eruption according to physical laws that haven't changed since the Earth formed. And when the next one comes, and it will come, our survival will depend on the same qualities that saved our ancestors: adaptability, cooperation, and the stubborn human refusal to go extinct no matter how bad things get. We're the species that survived Toba, that survived the Yellowstone eruption 640,000 years ago. That came through 117,000 years of near extinction and emerged stronger, smarter, more capable than before. We carry those survivors' genes, their intelligence, their resilience. We are the latest generation in an unbroken line of humans who refuse to die even when death seems certain. The question is whether we're smart enough to learn from their example, whether we'll build the resilient, cooperative, distributed systems we'll need to survive the next great crisis, whether we'll prepare while we still have time, or whether we'll wait until the sky goes dark again and we're forced to figure it out under emergency conditions. Because make no mistake, the volcanic planet we live on isn't done with us. The magma chambers are building. The pressure is accumulating. Somewhere, maybe tomorrow, maybe 50,000 years from now, the Earth will remind us again that we're not in control, that nature operates on scales and timescales that make our civilizations look like mayflies. That survival is never guaranteed, never certain, always contingent on our ability to adapt to conditions we didn't choose and can't control. But if history teaches us anything, it's that humans are really, really good at surviving. We're the species that looked at a volcanic winter and said, "Not today." We're the descendants of people who endured conditions we can barely imagine and refuse to give up. That legacy is still in us, still part of what makes us human. The fire that forged our ancestors isn't finished forging us. The volcanic planet we live on will test us again. The only question is whether we'll face that test with the wisdom of survivors or the complacency of people who've forgotten what we're capable of enduring. Our ancestors survived because they had to, because the alternative was extinction, and they chose survival, generation after generation, for hundreds of thousands of years. We're here because of those choices, because they refused to give up even when everything seemed hopeless. We owe them the same stubborn determination, the same commitment to survival, the same willingness to adapt, cooperate, and endure whatever comes next. Because the planet isn't done with us yet, and we're not done being human. Here's what it all comes down to. Every single catastrophe we've talked about, Toba, Yellowstone, Campanian Ignimbrite, they were disasters, unimaginable disasters that killed vast numbers of people and pushed our species to the very edge of extinction. But here's the thing, they didn't destroy us, they made us, because those 10,000 survivors huddling in tropical refuges after Toba weren't just lucky. They were the ones who could cooperate when cooperation was the only option. They were the ones who could innovate when innovation meant the difference between eating and starving. They were the ones who could look at 6 years of volcanic winter and somehow find the will to keep going, to have children, to pass on knowledge, to believe that tomorrow might be better than today. And they were right. Not immediately, not within their lifetimes. But eventually the skies cleared. The rains returned. Life came back. And when it did, their descendants exploded across the planet like nothing the world had ever seen. From 10,000 to 100,000 to millions to billions. Today, 8 billion people walk this planet. Every single one of us carries genes that survived multiple supervolcanic winters. Genes selected for intelligence, cooperation, and sheer stubborn refusal to give up when everything seems lost. Think about what that means. When you solve a difficult problem, when you figure out how to make something work against the odds, when you find a way to help someone else survive a crisis, you're not just being clever. You're expressing traits that were literally burned into your DNA by volcanic fire and ice. Your ancestors survived because they could do exactly what you're doing now. They could think, adapt, cooperate, and refuse to quit. The archaeological record shows it clearly. Before Toba, human technology advanced slowly, new innovations appearing maybe once every 10,000 years. After Toba, the pace accelerates dramatically. New tool types, new hunting strategies, new ways of processing food, new forms of social organization, all emerging within a few thousand years. The crisis hadn't just killed people, it had selected for the kind of minds that could innovate rapidly under pressure. And it's not just ancient history. The capacity for rapid innovation that got us through volcanic winters is the same capacity that let us develop agriculture, build cities, create written language, invent computers, and put humans on the moon. Every major achievement in human history traces back to cognitive abilities refined during those desperate millennia when survival itself was uncertain. But here's what's really important to understand. This story isn't over. We're not looking back at some finished chapter in human evolution. We're living it right now. The planet beneath your feet is just as volcanically active today as it was 74,000 years ago. Yellowstone is still there, still building pressure. Toba is still there, still capable of another massive eruption. New supervolcanoes are being discovered all the time. Scientists recently identified several potential supervolcanic systems that nobody knew existed even a decade ago. Sometime in the future, maybe tomorrow, maybe 100,000 years from now, another supervolcano will erupt. Another volcanic. Winter will test humanity's ability to survive, and when it does, the same traits that saved our ancestors will be tested again. Our capacity to cooperate across differences, our ability to share resources when they're scarce, our willingness to preserve knowledge and pass it to the next generation, our refusal to give up hope even when the sky itself seems to be ending. We are the descendants of survivors. We are the products of the worst environmental disasters in human history. We carry in our genes and in our cultures the accumulated wisdom of people who faced extinction and refused to accept it. That's not just history. That's who we are. That's what makes us human. So the next time you face something that seems impossible, the next time the world feels like it's ending, the next time you wonder if you have what it takes to get through a crisis, remember, your ancestors survived volcanic winters that lasted for years. They survived when 99% of the human species died. They survived when the world itself seemed to have turned against them. And they didn't just survive, they thrived, they built, they created, they became us. The fire that forged us is still burning beneath our feet. The story is still being written. And every single person alive today is proof that sometimes, when everything goes wrong, humans can be tough enough to keep hope alive until the world becomes livable again. If this journey through our species' most desperate hours has moved you, inspired you, or taught you something new, I'd love to hear about it. Drop a like if you made it this far. Leave a comment telling me where in the world you're listening from, and if you want more stories about how crisis and disaster shaped the world we live in, hit that subscribe button. Because we're all survivors. We're all descendants of the people who refuse to quit, and that's worth remembering.